Welcome my friends, welcome to my next lecture. Now in my last lecture I was talking about what is called one of the beautiful theorem in complex analysis, that is called Cauchy's integral formula. Now the plan for today's lecture is to talk about Cauchy's integral formula for derivatives. Now this is again one of the very powerful and beautiful theorem in complex analysis, because I already discussed this kind of importance of this theorem, because in real analysis you know what is the kind of you can say that a function is nice. That means you can say that if my function is differentiable, right? That's the meaning of nice in real analysis. Now but in real analysis you know there are plenty of functions where my function is 1 times differentiable, maybe twice differentiable but not thrice differentiable, or maybe 4th time differentiable but not 5th time differentiable. There are plenty of examples are there. Okay, so that means only the 1 times differentiability or 2 times differentiability will not allow you to talk about that whether my function is infinitely many times differentiable or not. So there are plenty of examples you will have it. However, compared to the complex analysis case, what is the nice functions if I say? So one of the way you can think about a function is nice is nothing but my function is analytic. So therefore you will see if I have analytic functions f, then I already discussed this kind of observation that analyticity of f implies my function should be infinitely many times differentiable. That means the property analyticity in case of complex valued functions of complex variable, it's very rigid. Okay, so therefore it will imply very nice observation that it will infinitely many times differentiable, not only that each derivative even it's analytic. So this theorem actually I am going to talk about, this theorem actually will come as a consequence of something, and that consequence is nothing but what is called consequence of some theorem. And what is that theorem? That is theorem is known as what is called Cauchy's integral formula for derivatives. So my plan is to talk about Cauchy's integral formula for derivatives for today's lecture. Now if time permits, then I will go what is called another nice theorem, what is called as an application of Cauchy's theorem, that is called Cauchy's estimate and Liouville's theorem. Okay, so as I said, so let me just start with Cauchy's integral formula for nth derivative. That's what I have written the title, Cauchy's integral formula for nth derivative. So that means this theorem tells you that the value of the nth derivative f n z can be represented by certain contour integral involving my functions f, z on C. So now if I just compare with the earlier Cauchy's integral formula, so there you will see if I have a functions f which is analytic in a simply connected domain, if I take a simple closed contour positively oriented, if I take a point interior to C, then I can evaluate or I can get the value of f at z naught by evaluating the integral. That means if I know my functional value on the contour, I can get the value of the functions in the interior. Now this is something more. It is said that not only you can have the value of the functions, but you can have the value of the derivative of your functions. That means not only f of z naught, but rather fn of z naught also you can evaluate if I know my value of the functions on the contour by performing some contour integrations. Okay, so now two things are there. So first of all, if I start with an analytic functions, earlier I will have the value of the functions at z naught, but now this time what will happen? Derivative. That means first of all I have to say that yes, f is analytic means f is differentiable, so therefore derivative at the interior point you can evaluate in terms of the contour integrations. But when I will talk about that f double prime or f triple prime, so two objects are there. First of all, I have to ensure you that yes, analyticity implies differentiability of infinitely many times. That means if f is analytic, of course by definition it is differentiable, but whether it is twice differentiable, whether it is thrice differentiable. So first you have to say that yes, nth derivative of f exists if my f is analytic on a nice domain. Not only that, nth derivative of f, evaluations of the nth derivative of f at some point z naught which is interior to a simple closed contour, I can evaluate that value, or I can get the value of the nth derivative of f at that point by evaluating some contour integrations. In other words, if I know my value of the functions on the contour, then I can have the value of the nth derivative of f at an interior point. So that is very important. So two things are there. First, I have to ensure you, yes, analyticity implies that my functions is nth differentiable for any n, and on top of that I can have the expressions of the nth derivative of f at some point in terms of what is called contour integrations. Okay, so that's the theorem. So let f be analytic in a simply connected domain D, let C be a simple closed positively oriented contour lies in D, then f and z denote the nth derivative of f. So if z naught is a point lies interior to C, first object is that nth derivative of f at z naught exists. that one has to ensure, yes, nth derivative of f at z naught exists. Not only that, I can have the expression of the nth derivative of f at z naught in terms of the contour integrations of f divided by z minus z naught to the power n plus 1. Now, in case if I take n is equal to 0, I will have exactly equal to what is called Cauchy's integral formula. That means f of z naught, because f of 0 is f, then you will have factorial 0 is 1 by twice pi I integration c f of z divided by z minus z naught dz. So this is actually what is called for the extension. That means you can think about, this is actually generalization of what is called Cauchy's integral formula. If I put n is equal to 0, I will have the what is called Cauchy's integral formula. So therefore this is the one. So therefore f of n z naught, this is factorial n divided by twice pi I, f of z divided by z minus z naught to the power n plus 1, and therefore this is n from, okay, this is for the derivative onwards, n 1 to 3. Here I am including n is equal to 0 by pretending that f of 0th order derivative of f is the nothing but the functions f of itself. So therefore this is called what is called Cauchy's integral formula for nth derivative. Okay, so therefore if my function is analytic in a simply connected domain, and if I take a simple positively oriented closed curve inside my domain, so therefore the same picture will be there. This is my D. So this is my simple closed positively oriented contour C. Take a point z naught interior to C. Then the nth derivative of f at z naught. Of course, I have to first ensure you that yes, my function is nth differentiable, and the nth derivative of f at z naught, I can have the value in terms of the contour integration C f of z divided by z minus z naught to the power n plus 1 dz. Okay. Okay, but of course to prove this theorem, of course proof available in many books. What I will do, so instead, so f of z naught, so of course Cauchy's integral formula I already proved. So what I will do, only for one more derivative I will just tell you, look, if I take n is equal to 1, that means f prime of z naught, also you will have the expression in terms of what is called in terms of contour integrations. But once you have the f prime, then you can just repeat that process. You will have f double derivative, f triple derivative, so on and so forth. So only one n is equal to 1 I will prove it, and rest you just take it as an exercise and prove it using inductions. Okay, I am not going to prove it. So only for n is equal to 1 I will prove it. Okay, so now Cauchy's integral formula for higher derivatives. As I said, I will just calculate f prime of z naught. So I will calculate f prime of z naught, which is what is called 1 divided by twice pi I fz divided by z minus z naught to the power square. So that formula I will prove it, and rest you should do it by inductions. Okay. Now since my function is analytic, so therefore it is differentiable. So therefore derivative at the point z naught, this is the formula you can have it. Limit h approaches to 0, f of z naught plus h minus f of z naught divided by h. Okay. Now what I will do, so now what is this? So therefore now you can just draw a picture. So suppose this is my D. So this is my simple closed contour C. Suppose this is my point z naught. Then what I will do, I will just part up my point z naught little bit, so that z naught and z naught plus h both lies interior to my contour C. So that's kind of, you can I can think, because h approaches to 0, right? So therefore if h approaches to 0, z minus z naught plus h approaches to z naught. So therefore if I take h is very small, so that z naught and z naught plus h both lies interior to C. That's kind of assumption I am taking. So this is the limit. Then what I will do, so then I, using Cauchy's integral formula, I know the value of the functions at z naught in terms of the contour integrations. Also I know the value of the functions at z naught plus h in terms of the contour integrations. And what is that? This is 1 by twice pi I integrations over C fz divided by z minus z naught dz. And what is that? This is 1 by twice pi I integration C f of z divided by z minus z naught plus h dz, right? So two expression I know in terms of contour integrations. Do the algebra or properties of contour integrations. If I combine it, so 1 by twice pi I h, that factor will come out, and then in the contour integrations you will have the object fz divided by z minus z naught minus h. Okay, so this is the one, and this is fz divided by z minus z naught. Now with a caution that C is chosen in such a way so that the point z naught is, of course it is there, z naught plus h also enclosed. That means both z naught and z naught plus h are lies inside the contour. Then do the algebra. In this object I can write, this is limit h approaches to 0, f of 1 by twice pi I h times f of z h divided by z minus z naught minus h times z minus z naught. Now what I want that this limit, if I want to get the formula, right, f prime of z naught should be twice pi I integration C fz divided by z minus z naught square dz. Okay, so that's what I have to prove. So this limit, I will show that this limit is exactly equal to this one. Now a priori we can say that yes, if h approaches to 0, somehow this get cancelled. So this h get cancelled. So this will get cancelled, right? And if h approaches to 0, somehow this is z minus z naught, this is also z minus z naught. So at the end you will have this kind of formula. But this is the guess. But to prove that it is exactly this one, then I have to use the analysis part. That means I have to use the analyticity of f or differentiability of f. Okay. So my target is that this limit, I will show that this is exactly equal to this one. So since I know what will be my limit, then what I will do? I will say that okay, this minus this, what I will do that? Well, 1 by twice pi I h, then c of this object fz h divided by z minus z naught minus h times z minus z naught minus 1 by twice pi I integration c fz divided by z minus z naught square dz. I will estimate this object and I will show that this is goes to 0 as h approaches to 0. Then I am done. That's the only thing I have to do. Okay. So that's what I have done. So we need to prove that this object, this is the limit as h approaches to 0, should be exactly equal to this, right? So therefore I will just estimate this minus this. That's it. So that's what it is. So 1 by twice pi I factor, you can just don't kind of forget about it. Well, this h is cancelled, so therefore actually this is 1 by twice pi I. Okay, so you do not care about this. This h get cancelled, so therefore 1 by twice pi I fz divided by z minus z naught minus h times z minus z naught should goes to this one. That means I have to estimate. So this h gets cancelled. Therefore I have to estimate 2 pi I is a constant. Forget about that. So therefore this integration over c fz divided by z minus z naught minus h times z minus z naught minus fz divided by z minus z naught square, I have to take the absolute of that and I will show that this goes to 0 as h approaches to 0. So that is exactly I have written. So this contour integrations where this is first one is the fz divided by z minus z naught minus h times z minus z naught, and the second one is fz divided by z minus z naught square. Again, do some algebra by properties of contour integrations. It turns out that this is exactly equal to contour integrations of fz h divided by z minus z naught h times z minus z naught square. Now you can have all the formula, right? I have to use ML formula or I have to use what is called contour integration, definition of contour integrations, and I can show that yes, this is dominated by some constant times h. Now since h approaches to 0, then I am done. I will show that this is dominated by some constant k times h or mod h, and this is goes to 0 as h approaches to 0. That's the target. Now look at the object. So I have to estimate this one. So therefore somehow if I use what is called definitions of contour integrations, I can push the modulus inside the integrand, and I have the integrand is this one. So somehow I have to estimate it. Now if you remember this kind of estimate, if I have like something in the denominator and something in the numerator, okay, some object, I want to show that this is dominated by something. So the top one, it is okay, I have to show the upper bound of that numerator, but the denominator, what I will do, this should be not the upper bound but the lower bound I need it. So therefore I have to somehow estimate this object z minus z naught minus h times z minus z naught square. This should be greater equal to something, so that if I take the reciprocal of that, this should be dominated by something. So that's the target. Okay, so what I will do, so I have to use ML inequality. What is the ML inequality? If you remember, ML inequality means if I have this kind of contour integration gz dz, then this is dominated by m times l. What is l? L is the length of the contour C, and what is my m? M is the supremum. M is, you can say that this is supremum of modulus of g of z, where z running over my contour C. So somehow if I say that the supremum is dominated by something, then it should be that m times l. So that kind of formula I will use. So that means somehow I need to check whether the integrand, can I have an upper bound of the integrand. So numerator, of course you will have upper bound, but the denominator, to get the upper bound of the whole integrand, in the denominator I need the lower bound, so that if I take the reciprocal, we will have the upper bound. That's the target. Okay, so first observe that your functions f is dominated by some constant m for all z running over C. This is true. Why? Because C is a simple closed contour, so you can think about it as a compact set. My function is analytic, that means it is a continuous functions. So continuous functions on a compact set, it is bounded, so therefore you will have a bound. So therefore using that one, you can have it f of z is dominated by some constant for all z running over the contour. That is the first one. Second one is that what I will do, so if I draw a picture, you will see if I draw a picture, so it says that, So this is my picture. So suppose this is my domain, this is my C, right? This is my C. So this is Z0 is there, this is some Z0 plus H is there, right? So what will happen? So since C is a simple positively oriented closed contour and Z0 and Z0 plus H are sitting inside, so therefore I can take a distance Z0 from any point of C, okay, because Z0 is the interior to C, so that's exactly I am doing. So I am considering Z minus Z0 absolute, so that means take any point and Z minus Z0 where Z running over C, and I am saying that take the minimum. Since Z0 is the interior to C, then you will have the minimum, and since Z0 is lies interior to C, so minimum should be positive, so that means alpha should be positive. That minimum will exist and minimum will positive, okay. And the important fact is that if alpha is positive, so therefore since alpha is the minimum, so therefore Z minus Z0 mod square, which is greater or equal to always alpha square. So you can by pictorially you can see. So if I Z0, so what is the minimum? This should be, this is the minimum one. Whatever distance I can take Z0 from the contour of the point of the contour, so this is the minimum distance, and suppose this is my alpha, and alpha is positive because Z0 lies interior to C. So, and if alpha is positive, then you will have this kind of inequality. So if Z running over what is called the contour on the contour C, the Z distance between Z and Z0 absolute square, which is greater or equal to alpha square, where alpha is positive because minimum will exist and minimum will positive because Z0 is lies inside the contour. That is the first fact. Second fact is that yes, since it is the minimum, of course alpha is lesser equal to Z minus Z0, that is clear because alpha is the minimum of the distance between Z and Z0. Then this is by triangle inequality Z minus Z0 plus H minus H, which is dominated by Z minus Z0 minus H plus mod H, that will have it, okay, that I can do that. So therefore alpha is dominated by Z minus Z0, which is lesser equal to Z minus Z0 minus H plus modulus H. But you see in the, so that means what? That means you see in the denominator you will have Z minus Z0 square factor times Z minus Z0 minus H. So this factor is dominated by alpha square, it is greater equal to, right? That means it is lower bound I am getting. What about this one? There also I need the lower bound. That means in the denominator both factor I will have a lower bound, then if I take the reciprocal I will have the upper bound. And this kind of problem I already discussed. What I am saying is that, so now what you will do this kind of object, okay. So this kind of tricks you should know, okay. What is that? Now in the denominator you will have this factor Z minus Z0 minus H, right? What is that? This is Z minus, so this is Z minus Z0 minus H. Now modulus of A minus B, which is greater equal to modulus of mod Z minus Z0 minus mod H. So this kind of inequality I have already proved in my beginning of the lecture. So modulus of Z1 minus Z2, which is greater equal to modulus of mod Z1 minus mod Z2. If I use that fact, now look, so this is equal to this, which is greater equal to this minus this. But what is Z minus Z0 mod? This is always greater equal to alpha. So therefore this is greater equal to alpha. Now look at the modulus of H. Now if mod H is lesser equal to alpha by 2, then what is minus of mod H? This is greater equal to minus alpha by 2. So therefore I can say that this is alpha minus mod H, and this is greater equal to alpha minus alpha by 2, and which is alpha by 2. Clear? So therefore this is the way. So therefore this object, which is same as difference of two complex number, which is greater equal to modulus of this minus this, but mod Z minus Z0, which is always greater equal to alpha. So that means I have to somehow estimate this object. But if I assume that mod H is lesser equal, because H is in my hand, right, because H is approaching to 0. So therefore since alpha is fixed, so therefore I am taking H in such a way so that modulus of H is lesser equal to alpha by 2. Once I have that fact, then this object is greater equal to alpha by 2. Now in the denominator I have two factors. This is also greater equal to alpha by 2, and this is greater equal to alpha square. So therefore if I take the reciprocal, which is dominated by, what will happen? Which is dominated by 1 by alpha by 2 times alpha square, and in the numerator f of Z times H, that is f of Z is dominated by M, so therefore you will have M times mod H. Now you see M is constant, alpha is constant, so therefore this is some constant times H. Now this is goes to 0 as mod H goes to 0. So therefore I am done. So therefore by Mn inequality you have these 4 observations. This is the boundedness of A, this is the distance between point Z on the contour from the Z0, this is the inequality because alpha is the minimum, and this is the one. If I assume that mod h is lesser or equal to alpha by 2, then the corresponding one of the factor of the denominator is this is the corresponding upper bound. Another factor upper bound is this one. If I use this fact and Mn inequality, I can estimate this contour integrations by the numerator is dominated by m times mod h, denominator is dominated by alpha by 2 times alpha square, and then what will remain? The length of the curve. Length of the curve, I am saying the length of the curve is small l. So small l is nothing but the what is called length of the curve C. So since if I assume that small l is the length of the curve, so therefore length of the curve times the what is called this object. If it is dominated by some constant, then supremum is also dominated by that one. So therefore this estimate I can have this at the factor. So you do some algebra, then you will end up with this kind of factor. Now look at this expression. 2 is constant, m is constant, l is constant, alpha is constant. So therefore now this estimate is dominated by some constant times mod h, and this is goes to 0 as h approaches to 0. Now this is therefore this is goes to 0 as h approaches to 0, but this estimate means what? This minus this goes to 0 as h approaches to 0. So therefore limit of this object is exactly equal to this one. So therefore you conclude that by as h approaches to 0, you will have this kind of formula. So therefore you can say that is as h approaches to 0, this s goes to 0. So therefore I will have the formula f prime of z naught, which is 1 by twice pi I integration c f of z divided by z minus z naught square dz. Then I am saying that by repeating exactly the same technique, you can also say that my function is twice differentiable, and derivative of twice difference value of the second derivative of f at the point z naught will have this kind of what is called contour integrations. So this is factorial 2 divided by twice pi I integration c fz divided by z minus zq times dz and so on. Okay, so that's how. So therefore now you see, so then you can say that how I can check. Now you see the if I take n is equal to 1, that means you have the value of the functions at the point z naught, derivative of f at the point z naught in terms of contour integrations, 1 by twice pi I fz divided by z minus z naught square dz, right? But look, if I see the picture, so this is my domain, this is my contour C. So if I have a z naught, you will have the value. Similarly, if I take a small point and if I perturb the point z naught, say suppose z naught plus k, there also I can take the I can have the value z naught plus k. So therefore whatever point I can take which is interior to C, I will have the value of my derivative at that point. Once I know my value of the functions of derivative at each point, then I can calculate the second derivative, because second derivative, if I check second derivative at the point z naught, what is this? This is limit h approaches to 0 f prime z naught plus h minus f prime z naught divided by h. But unless and otherwise I do not know the value of f prime of z naught plus h and value of f prime at z naught, I cannot calculate. But just by the I have explained that the derivative of f at a point z naught, and z naught is the interior to C, you know the exact expression in terms of contour integrations. So therefore you know the expression of this, you know the expression of this, then again by repeating the same process, so that this limit will exist, and this is exactly equal to 1 by twice pi I integrations over C f of z divided by z minus z square q dz. So therefore now in the second step, you will have, you know the value of your second derivative at each point inside the contour, then you go for the third derivative. Third derivative you can write in terms of second derivative, do the same process, you will have the formula. Then for fourth derivative and so on and so forth. So if I go like that, then at the end of the day I can conclude, yes, if I start with analytic functions on a simply connected domain D, then I first will conclude that yes, my function is infinitely many times differentiable, and if I take a point z naught in my domain, and if I take a simple closed positively oriented contour where z naught is lies interior to C, then I will say that nth derivative of f at z naught I can write in terms of contour integrations. And what is that? This is 1 by twice pi I, then contour integrations over C fz divided by z minus z naught to the power n plus 1 dz. So you have to be little bit careful about the expression. This is very important. Though I am talking about in the left hand side nth derivative, but in the denominator of the integrand it should deal with n plus 1. So you should be careful, and in the constant factor, you'll have a n factorial. So you have to be careful those kind of expression. You should not say that, okay, I am dealing with n derivative, so here also n is there. No, you should be careful, okay? It should be n plus 1. Now once I have Cauchy's integral formula for nth derivative and the expression of nth derivative at some point z0, then many problem you can solve it, right? For example, if I say that, okay, calculate, this is applications of Cauchy's integral formula for nth derivative. If I say that calculate this kind of object, what will you do? E to the z divided by z to the power 4 and then mod z is equal to 2. Now then I have to apply Cauchy's integral formula for nth derivative, but before that I have to identify what is my function shape, what is my domain, and at which point I would like to calculate. So this kind of problem, either you can say that since C is mod z is equal to 2, as I said, you know what is your parameterizations, gamma of t is 2 times e to the I t runs from 0 to 2 pi, and do the calculations, you can do it. But instead of doing that one, just looking at the integrand, you can see if I just apply the definitions, it will be very difficult to calculate. Rather, I will use what is called Cauchy's integral formula for nth derivative. Then you have to identify what is your contour. Let's see whether, first you have to say that what is your contour, what is your functions, then I can apply Cauchy's integral formula for derivative. So here you can see what is your contour, mod z is equal to 2, so this is my contour, mod z is equal to 2, okay. What about the singularities of this integrand? 0 is the singularity which is sitting inside my mod z is equal to 2, perfectly all right, right? Now to apply Cauchy's integral formula, I will say that, well, I have to identify what functions. Here my functions I am taking e to the power z, which is analytic everywhere in the complex plane. Now I can write this object which is integration c f of z divided by z minus 0 to the power 4 dz. And what is that? This is integration c f of z divided by z minus 0 to the power 3 plus 1 dz. Now you see, you have a functions f, you have a contour, 0 is sitting inside. Now what is this value of this contour integrations? By Cauchy's integral formula nth derivative. Now since n is equal to 3, so I will say that now this is same as third derivative of f at 0, then there is a factor. What is the factor? As I already told you, the factor is this one, factorial 3 divided by twice pi I, and this should be in the right hand side, you have to bring it to here. So therefore it will be like this one. What is that? This should be twice pi I divided by factorial 3. So this will give you the value of your these integrations. So but you know the functions f, so then you can have the value of third derivative of f at 0 and with that factor, very easy. So I have written clearly, so your f of z is exponential z. Observe that f of z is analytic and inside mod z is equal to 2 by applying Cauchy's integral formula, because 0 is sitting inside or interior to mod z is equal to 2. Now nth derivative, so that means first you have to identify how I can write it and then look at the hypothesis of Cauchy's integral formula for derivatives and apply it. So therefore, by Cauchy's integral formula, third derivative is exactly equal to factorial 3 divided by twice pi I times this. So I want to calculate this value. So this is nothing but this is exactly equal to twice pi I, the third derivative of f at 0 divided by factorial 3. If I calculate it, this is okay. Because what is my function? Say f is exponential. So you take the derivative, it will give the same functions e to the z. So what is the evaluation? It will give you 1. So it turns out that this is 2 pi I divided by factorial 3 means 6, that means this is pi I by 3. So this exercise I have, you can, so the advantage is that, so you can, since you know what is your contour, you know the parameterizations, you can calculate explicitly using the definitions. But looking at the integrand, it is very difficult. So therefore, to have or to calculate the value of the contour integrations, you use what is called Cauchy's integral formula for nth derivatives. Again, because by looking at the factor in the denominator, you can guess, well, I have to apply not Cauchy's integral formula, but Cauchy's integral formula for nth derivative. So then you have to just write appropriately and identify your functions, identify your contour, look at which point is the singularity of the integrand sitting inside your contour, apply Cauchy's integral formula for derivative and get the conclusion. So this is one exercise I have given. I didn't kind of write what will be the value. But suppose if your contour is circle of center z0 radius r, then you can explicitly calculate this object. So you should kind of do it. Well, there are two ways you can do that. First, you can just directly use. So if I just, because this is a circle of center z0 radius r, so therefore what is the parameterization? z0 plus r e to the it and t runs from 0 to 2 pi, right? So using these parameterizations, you can directly calculate it. This kind of problem I have already discussed in my last class. earlier lectures. But also you can use what is called Cauchy's integral formula for derivative, because you see this object I can write dz divided by z minus z naught, then you have n minus 1 plus 1, right? And then what is your function f of z? F of z is exactly equal to 1. No? So now you apply what is called Cauchy's integral formula for derivatives, because what is a one line calculation, okay? So this is okay. So because f of z is constant functions 1, so therefore, and this is n minus 1 plus 1, so what is the, if I use the Cauchy's integral formula for derivative, that means I have to calculate the derivative at the n minus 1 times of my function f, and then I have to evaluate at that point z naught, and then there is a 2 pi I or n factorial will be there. So therefore, okay, maybe just I can calculate it, this would be easy actually, okay, so one line proof actually. So I say that, okay, this is same as integration c f of z dz divided by z minus z naught to the power n minus 1 plus 1, okay. What is your f of z? F of z is 1. Constant functions 1 is analytic everywhere, okay. So therefore, by Cauchy's integral formula for nth derivative, in fact actually here it will be n minus 1, the value of this integration should be, what will happen, since I am dealing with n minus 1, so therefore it should be 2 pi I divided by n minus 1 factorial times n minus 1 derivative of f, and I have to evaluate at the point z naught. So that will be the value of this, what is called contour integrations. But what is your function f? F of z is 1. So therefore you will see, if n minus 1 is non-zero, that means since I am dealing with constant functions, so therefore the derivative always vanishes. So therefore it will be actually 0 for all n minus 1 which is non-zero. Correct? Well, there is a catch actually, very nice at the same time. So because since I am dealing with n is equal to z, you can say that n has two possibilities, either n is positive or n is negative. Now if n is negative, look at the integrand, then what will be that integration? Integration c z minus z naught to the power, if n is negative, that means if I take this one, so therefore n is negative means what? This should be minus of n dz. And minus n is negative means minus n is positive. So therefore z minus z naught to the power some positive power. Now what is z minus? It's a polynomial, na? F of z is equal to z minus z naught to the power n, and n is positive. Okay. So therefore this is a polynomial functions of z. So this is analytic functions, analytic everywhere in the complex plane. And what is this contour? It's a simple closed contour centered z naught radius r. Now if I have a function which is analytic everywhere in the complex plane, and if I take a simple closed contour, what is the value of this integration? Should be 0 by Cauchy-Gustard theorem. So therefore, if n is negative, you do not care. By Cauchy-Gustard theorem, this integral value is only 0. So only fact you should care that if n is positive. So if n is positive, strictly greater than 0 or say greater or equal to 1, then what will happen? You see, it will have a singularity at the point z naught. Because if n is equal to 0, it is constant function 1. So n is equal to 0 means what? It is integration c dz. Again, by Cauchy-Gustard theorem, this is 0. So therefore, only fact you should consider is n is greater or equal to 1. So that means n minus 1 should be positive, right? This is the fact. Now, if n minus 1 is strictly positive, that means if n minus 1 is greater or equal, that means n minus 1 which is greater or equal to 1, that means the by Cauchy's integral formula for nth derivative, the value of this integrations is the derivative of f at the point z naught, or that many derivatives. Since it is n minus 1, it should be n minus 1 derivative of f. But what is your f? F is a constant function. If n minus 1 is greater or equal to 1, so therefore this object is always 0, so therefore this is 0. So this is also 0 if you say that n minus 1 is greater or equal to 1. That means n is greater or equal to 2. So that means only the fact is remaining is n is equal to 1. If n is equal to 1, that means this is f0. What is f0? f0 means the value of the functions at the point z naught. So therefore value of the functions at the point z naught means what? It is 1, because f is constant functions. So therefore only at n is equal to 1 the functions will survive. And what is the value? Value will be twice pi I. So this kind of observations I already discussed. So therefore this is 0. So at the end you can conclude that, whatever discussion I have done it. So you can say that this is actually 0 for all n not equal to 1, and this is twice pi I if n is equal to 1. So if you remember, if I use the parameterizations of my contour, you can do that, so not an issue, but maybe it will take some time to evaluate it. But rather, if I just interpret these integrations or contour integrations or to write in the form of Cauchy's integral formula for nth derivative, and then identify what is your contour and what is my function's f, then you can easily calculate. Okay, so well, this is very nice. So depending on n, so if n is negative, then of course the integrand 1 by z minus z naught to the power n. If n is negative, then the integrand is analytic, so therefore by Cauchy-Goussard theorem it is 0. If n is positive, so if n is greater or equal to 1, then it will have a singularity at the point z naught. Again, using the Cauchy's integral formula for derivative, you can identify that your integrand, that means the functions f, what is there in the statement of Cauchy's integral formula, it is a constant function 1. So therefore if I take the derivative, it will be 0. So therefore evaluation also 0. So therefore if n is greater or equal to 1, that means the n is strictly greater than 1, that means n is greater or equal to 2, that means I am done. So only the fact is remaining, n is equal to 1. N is equal to 1 means, so just to identify that it should be n minus 1 derivative, and since n is equal to 1, that means n minus 1 is 0. So therefore f of 0 then means value of the functions at the point z naught, and since f is 1, so therefore this is 1 times twice pi I. So therefore this is one of the way to evaluate this kind of integrations. Though I have given as an exercise, but actually I have proved it. In fact, that is one of the easiest way to prove what is called this kind of problem, instead of just writing your what is called contour in terms of parameterizations and using the definitions of contour integrations. Okay, so another 2 examples I am saying. So for example, if I calculate this kind of object, so this, what is this again? What is the contour? Contour is unit circle, right? So what is the functions? F of z, what is this? This is e to the z divided by zq. So what are the singular points? Z is equal to 0, which is inside my what is called interior to my circle of radius 1. Well, this kind of problem I have already done it. This is z to the power 4, so this is done. So therefore this is also you can calculate, this is I pi. Now come back here. So this is one of the another problem. Here of course your integrand contour is different. So this time contour is centered at 1 and radius is more than 2, 5 by 2. So therefore it should be like that. So what are the singularities are there? So singularities are 4 and minus 1. 4 and minus 1. But you do not care about what is called 4, because 4 is stay outside from your contour. So only fact is that minus 1, which is sitting inside. So therefore you do care about minus 1. So what I will do, so this object you can write integration z minus 1 is equal to 5 by 2, then fz divided by z minus of minus 1 to the power 4, and what is your f of z here? F of z is, you can have 1 by z minus 4. Now this f of z is equal to 1 by z minus 4, then you can say that, say, because it is a circle of centered 1 radius 5 by 2, so that means 4 will be here. So this is okay, so centered at 1, okay, 5 by 2 means what, 2 point something, right? So therefore it should be like this one, and your 4 will be lies here. So if since 4 stay outside from my contour, so therefore if I consider this kind of functions and if I consider this kind of domain, of course this domain, that distance between this and this should be positive. That means this domain should be away from 4 and minus 4. Okay. So if I consider this domain, in this domain my function is what? Analytic. Okay. And this is a simply connected domain. So and inside that I have this contour z minus 1 is equal to 5 by 2. Inside the minus 1 point is there sitting interior to this one, and I can write this object of the form fz divided by z minus of minus 1 to the power 4. Then also you can say that this is same as z minus 1 is equal to 5 by 2 fz divided by z minus of minus 1 to the power 3 plus 1. Okay, now I can apply all, it satisfies all the properties of Cauchy's integral formula for derivatives. So therefore it should be twice pi I times factorial 3. Okay, this is the one. Then I have to calculate third derivative of my functions 1 by z minus 4, and then I have to evaluate at the point z is equal to minus 1. You just calculate it, you will be able to do that. Okay. In summary, so if I just combine everything, it says that let C be a simple closed curve contained in a simply connected domain, f is analytic, then you can have the value of this kind of contour integrations. What is that? If fz divided by z minus z naught to the power n plus 1 If n is equal to 0, that means it is fz divided by z minus z naught. That means it is the Cauchy's integral formula. And what is the value? This should be twice pi I times f of z naught. Look, there is no factor here. So 1 by 2 pi I should be there. So it should be 2 pi I times f of z naught if n is equal to 0. If n is greater or equal to 1, that means this is the statement for Cauchy's integral formula for derivatives. That means this should be 2 pi I divided by n factorial f n z naught. And if z naught lies outside my contour, then of course these functions f of z, which is z minus z naught to the power n plus 1, and if your contour inside the point z naught lies outside the contour, that means inside the contour and on the contour this function is analytic functions, and therefore by Cauchy-Gusser's theorem this contour integrations over the simple closed contour should be 0 if z naught lies outside the region, because that time I can talk about the analyticity of my functions fz, which is exactly equal to 1 by z minus z naught to the power n plus 1. In other words, integrand is very nice, it is analytic. Then by Cauchy-Gusser's theorem, if I take a simple closed contour, value will be 0. So maybe this is the formula you should remember to evaluate this kind of what is called contour integration. So therefore, if I give some problem, somehow you identify it is of this kind of form where f satisfies, this is the hypothesis, then this formula will help you to get the value of the contour integrations. You don't have to calculate explicitly using the parameterizations, but if you somehow identify your functions, then you can evaluate it, these contour integrations. Okay, so I think that's all about what is called Cauchy's integral formula for nth derivatives or Cauchy's integral formula. Now in my next lecture, you will see there are nice consequential applications of Cauchy's integral formula will be there. For example, you will have Cauchy's estimate, you will have Liouville's theorem, you will have Morera's theorem. Maybe in my next lecture, I will at least start with applications of Cauchy's integral formula or Cauchy's integral formula for derivatives. I think I should stop here. Thank you.